Good morning. Well, I've got some sad news today. The heat pump compressor that you've seen me do previous videos on has finally died. I'm going to go through a step-by-step process where just with a multimeter and some common sense and a little bit of respect for your safety, you can make a confident diagnosis of failed heat pump compressor. I think this is going to be an interesting video. It shows some interesting insight as to how these systems are designed. I hope you come along. About 18 months ago, I did a video of how a failed run capacitor can cause a locked rotor presentation in this unit. And we diagnosed and swapped out the capacitor, and it's done fine since then over the last 18 months with no problems. But last Thursday I came home from hockey and I heard this. That's the sound of my wallet draining. The loud buzzing sound you're hearing is from the heat strips. They're used in two situations in a heat pump. Heat strips are nothing more than resistance coils, much like a giant toaster, in this case drawing about 80 amps of current at 240 volts. So what's that, almost 2,000 amps, or 2,000 watts. Heat strips are used in two situations in a heat pump. The first is defrost mode. When outside temperature drops below freezing, ambient moisture has a tendency to freeze on the outside coils. So to prevent that, when it's cold, the heat pump goes through a brief defrost mode for a few minutes every few hours. It's a modified air conditioning mode. The blower fan is set to low speed and the heat strips kick in so the furnace won't blow cold air around the house. The second situation is when the heat pump isn't able to keep up. The board is programmed to recognize this and bring in supplemental heat. So that night I came up here and I checked to make sure the system was set to heat, which it was. But there was a symbol up here saying that supplemental heat was needed. We've got a problem, Houston. By the way, if you ever notice that your heat pump isn't working, the very first thing you need to check is the thermostat. Notice how I can toggle through auto, heat, cool, and emergency heat. If somebody accidentally bumps the toggle into emergency heat right here, your pump's going to turn off. So before you call help for a technician, remember to check this so you don't look like a goof. In the winter, you generally want the thermostat set to heat. So the next morning, I took off the panel to get back to the board, and I found this trouble code. Now just count the flashes. 1, 2, 3, 4, 5. On the legend that says open circuit. So it says it's not getting enough voltage. So from here I went to the wires that are incoming, L1 on L2, put my multimeter on AC and measured voltage here, and we got 0 volts. So we're not getting any power to the unit. So from there I went back to the main fuse panel to see if the fuse was blown. So here we are in the main panel. This is the 60 amp breaker for the heat pump, and this is the 125 amp breaker for the heat strips. The heat pump breaker was blown. Now, a fuse never blows for no reason. There's a reason behind it. And so after some thought, I flicked it back on, and it didn't trip right away, but I heard a couple of clip sounds from the sub-panel across the hall. Let's have a look at that. Okay, here we are in the sub-panel across the hall, and these two circuits, both arc fault circuit interrupter circuits, were tripped. Now the interesting thing here is that neither of these circuits have anything to do with the heat pump or any of it. And so we know that there's something going on systemically. Either it's a ground problem or a neutral problem. Let's go back outside to the outside unit. So when I got back to the pump with power on, to my surprise, the outside fan was slowly turning, even though I'd turned the thermostat way down. I'm not going to reproduce that for you today. It's not good for sensitive electronics in the home, but it's further evidence to say that we've got some kind of a ground or neutral problem. So at this point, you got to be really cautious. There's serious evidence to say that you've got some kind of short to ground here going on, and so you could well have voltage somewhere that you're not expecting. And so what I did is I pulled the cutout out, I turned the breaker off, and even with that, you can see we've still got lights going on, and so there still could be voltage probably backfeeding from the thermostat here. But the important point I want to make is that you want to be really cautious and careful. Now, I went on to the next step, which I showed very well in the previous video when I replaced this capacitor. And basically, I unhooked all of the wires. I checked out the capacitor. There's no short to ground on the capacitor itself, and it's retained its function. And then I moved on to checking the 3 wires that lead down to the compressor. And I found, to my surprise, that the resistance between the start winding and common is 0 ohms as opposed to 0.6 ohms, which it was before. And secondly, all 3 of those wires are shorted to ground. Now the problem is that you don't know where that short has happened. You're really suspicious it's at the compressor, but it could be at the contactor here, or it could be on a frayed piece of sheet metal where a frayed wire has happened. And so what you want to do next is go right at the compressor, disconnect all of the wires at the compressor, and do your testing again right at the compressor. Let's do that now. Checking for resistance to ground. I got 54 ohms on that one prong. And we get 53, 54 ohms with all three of those prongs. So clearly the motor is bad. So as much as I hate throwing things away, we have to remember this system's almost 19 years old. It doesn't owe me anything, and at this point the most realistic strategy is just to replace the whole thing. We're getting this to that effect right now. So I hope this video helped you out. Let me know if I earned your like today. I'd love to hear any comments. Thanks for watching.